and they just, as I said, they were competitions that contributed to the field and effectively set a level playing field for everyone to build something new and kind of really drive us towards better systems. I'll now go through each of these in a little bit more detail. So starting with the simplest, rule-based methods. I thought it's easiest to explain this in terms of an example, and subject-verb agreement should be relatively straightforward. So if we have a sentence, the chicken crossed the road, a rule-based system might correct it as follows. So first, we can automatically part of speech tag and parse the sentence. That effectively adds these labels here, and the arrows show the relationship between the words. Once we have that information, we can find the n-sub, which is the noun subject of the verb. So we pull out chicken and cross, which I've highlighted with this purple arrow here. And then once we've done that, we can just look at the different part of speech tags and check whether they agree. So you would expect a singular noun to go with a singular verb, or a plural noun to go with a plural agreement verb. And so in the other two cases, we know there is an error, and then we can write a rule that just detects this and then corrects this. And there are tools that let you go, for example, I'm going to input chicken as a noun, and I would like the tool to output the plural verb, the plural form of that noun. Relatively straightforward. Now, of course, there are exceptions and complications. So if we have a sentence like the chicken and the duck is crossing the road, then we first look for the verb and it's crossing, but then we also need to recognize that there is an auxiliary verb is, and that's where the agreement falls. So there's an extra step there. But also we should know that chicken is singular and duck is singular, but together they form a plural subject. So then we have to check how many subjects there are in order to work out what the agreement should be. There's a similar problem when you have a relative clause like the chicken which hate cars crosses the road. Well, chicken agrees with crosses, but then you need to check that crosses, like there's the relative construction and what the subject of that construction is as well. Effectively work out what which is referring to. And then there are other exceptions with quantities, like $5 are a lot of money. I mean, dollars is a plural noun, but it's one of these exceptional words that takes singular agreement. $5 is a lot of money. So even rule-based methods can start to get a bit complicated. Now, that said, the advantage of rule-based methods is that they are usually precise and easy to customize. Because a human is designing them, the human can actively think about all the exceptions and how grammar works and come up with a way that makes the machine behave in the way we expect. This also means they are often simple to implement and run. One of the main advantages of rule-based methods is that they're interpretable, explainable. So some of these later methods might perform better, but they will not be able to tell you why a particular correction was made. With rules, you can look through the rules and go, right, this happened, like if this, then that. You can work out precisely why the machine made its choice. And rule-based methods also don't require annotated data. They just require human knowledge. So as long as you've got someone who knows how grammar works, they can write some rules. Disadvantages of rules are that they can become incredibly complex or specific. I started to give an example of subject-verb agreement there, how it seems straightforward to begin with, but can start to become more complicated when you consider some of the more exceptional cases. But also, so rule order matters and maintenance is complicated. So in the example I gave, I suggested that we should possibly change the number of the noun, but we could have also changed the number of the verb. And in the rule-based method, you can either do one or the other. It just means every time it comes across a subject-verb agreement mismatch, it'll either always change the noun or always change the verb. And in some cases, we might want to do one and the other, but rules make that very difficult to do. It's also the case that rules are unsuitable for some error types, particularly semantic errors. So it's very difficult to think of a rule that would change something like a strong computer to a powerful computer without listing out a rule for every possible word. And then that's just unrealistic. Finally, so rules also require language-specific knowledge. So as I said, you need someone who really understands the ins and outs of grammar. which can be hard to find, or at least that there's always exceptions that you need someone who really knows a lot about grammar. So next type, language models. So language models work on the principle that in context some words are more probable than others. So given these 4 sentences, they sell a big variety of products, they sell a wide variety of products, they sell a great variety of products, they sell a large variety of products. I hope you have some sense that some of these are better than others. Like, none of them are wrong, but personally I find wide variety the most likely here. And so this is effectively the kind of relationship that language models try to capture. And yes, so we use this property to work out like what is more probable, what is less probable, and if it's very low probability, it's probably an error that we might want to fix. So to give an example, I often work in home. Let's say we want to correct or make sure that prepositions are correct in a given context. So first you train a language model, and this could be very straightforward in terms of just what is the probability of in after work, or what is the probability of in after often work, and it increases in complexity there, but you can train it from a large amount of text, which is readily available on the internet. Then for prepositions, we'll define a confusion set or generate a confusion set. So in this case, we might just go, well, here is a list of 5, 10, whatever prepositions. Then we try each one in the context, score it with the language model, and get a score. So in this case, the lower score is better. That's how this metric works. So if we try in this model, we get 284. If we try at, it goes down to 98. If we try from, it goes down to 55. And if we try on, it goes down to 300. It goes up to 315. So this shows that in this context, from is the most probable word in that gap, but also at also fits and is also acceptable. That's a kind of problem with this approach, but it does show you how it can be used to detect, like you can convert a low probability word in a position to a higher probability word in a position. So pros and cons of language models. So the main pro is that it only requires native text, albeit lots of native text. Like the later methods require parallel text that's been annotated by humans, and that's much harder to come by. So this really is a good strength. Unlike rules, they can also correct all error types, including semantic errors. So if you notice that like the adjective strong in front of computer is pretty low probability, but powerful is much, much more probable, then you might want to make a change. They're also effective in a low resource setting. So as I said, you don't need annotated data. So in theory, you could just download, let's say, Vietnamese Wikipedia and use that as your training data and still build a decent error correction system. Language models are also versatile. So although they might not be used as the main error correction system in some cases, they often play a role. Like sentence scoring for probability is just a very useful way to evaluate language, and so even other models make use of that property. Now, disadvantages are that probability is not grammaticality. So the sentence I always like to use is I is the 9th letter of the alphabet. That's one of the very few cases when you can say I is and it's grammatical instead of I am. And language models will fail to pick that up and want to always change that to I am. Another one is rare words. So if depending on what data you're training on, rare words might not appear very frequently. The example I use is paraklausitheron, which is a very special technical term that relates to a very specific type of Greek poetry, but is still a valid word in English. And another thing is generating confusion sets can be hard. So we saw with prepositions, you can just define like 10 prepositions and try them in turn. But if we were trying to generate something in the gap, I ate the big then there are so many different words that could fit in there. It's very hard to know which one is intended. So that is a bit of a weakness. In the next one, so then we moved on to statistical classifiers. So in this case, the example is you might want to predict the form of every verb in a sentence, which I've highlighted in orange here. Now, step one is that you define the labels. So these 6 labels represent the different forms of verbs in English. So VB is infinitive, VBZ is third person present tense, VBP is non-third person, VBD is past tense, VBN is past participle, VBG is the gerund ing form. And effectively, we want to predict one of these for every single verb in the sentence. We will then define some features. So these features could be, well, what is the predicted pos tag of the current verb? Is the verb preceded by to? And this is a particularly useful feature because if the previous word is to, then it's highly likely that the verb, like the form of the verb, is either going to be an infinitive or a gerund. It's not going to be a past tense or anything else. Then you could also say, is the verb an auxiliary? What is the lemma of the verb? What are the surrounding words, the n-grams around the word? And effectively, you're just defining things near the verb that you think could be useful. And then once you've defined this information, you can train a machine learning model to predict the weights of each feature. There are lots of different types of model you can choose from. I've just listed a few here: logistic regression, decision trees, support vector machines. But effectively, all of them will learn for a given verb in a sentence, which information that we have given it is most important. Like if it's the preceded by to, then that's going to be a very useful feature for predicting infinitives and gerunds. And the other features might be less important. So it just works out how to rank them like that. And then ultimately the model will just output for each label or for each verb, what form do I think? If the form agrees with what the form the verb currently is, then nothing happens. If the form differs, then you can generate the correct form in a similar way to rule-based methods at the start. One of the main advantages of this is that it's more flexible than rules. So whereas with rules, you had to precisely define the relationship between, you needed to extract the part of speech, you needed to extract the pars and work out what to compare. For classifiers, you just go, I think the pos tag might be useful, I think the pars might be useful, I think other things might be useful, and then the model just works out how to relate them without having to explicitly define it. And they also, so like language model approaches, they only require native data technically. As long as you've got a good corpus that shows how correct usage can work, then the model can detect deviations from it. Although that said, if you do also have a few examples of like negative examples of verbs in the wrong place, then that also teaches the machine how to perform better. A disadvantage of statistical classifiers is that the feature engineering can also be complicated. So although it's more flexible than rules, you also need to think of what features or what aspects are relevant to each type of error you want to correct. They also typically work better for small confusion sets. So most work has applied confusion sets only to determiners, prepositions, and word forms, not like content words. But also each classifier only targets a single error type. So you would build one for determiners, one for prepositions, one for verb forms. And then like rules, we get the problem that classifier order matters. So if you correct all the verb forms first, and then the determiners and the prepositions, you're going to get different output than if you correct prepositions first, and then determiners, and then verb forms, which can be a bit of a problem because ideally we'd want everything to be consistent. It's also worth mentioning that in practice, classifiers have now kind of fallen out of fashion, so they're not really used so much these days. But they're still worth knowing about as a step in the journey towards more robust error correction systems. So the next one is machine translation. And in this case, the approach to error correction treats it as a translation from, let's say, bad English to good English. And it's a similar principle for both of the types of machine translation, so both statistical and more recent neural machine translation. And the main thing to know is that this is the first method that requires parallel data. So you need, like if you want to build a system for French to English, you need a corpus of sentences in French, and then also the corpus of equivalent translated French sentences in English, and then the model will learn how to translate one to the other. In this case, this means we require humans to have gone through a load of noisy text and fixed the errors, which is expensive to do. Once you have that, though, you can then train a model, and ideally you can then input any new ungrammatical sentence, and the model will output a corrected sentence. Exactly how this works is very detailed, so I won't go into it. But some other additional things that are worth knowing about, or tips and tricks for machine translation, is that because there is limited data, people often use artificial data. So you don't have to always get a human to correct something. Instead, you can start with some high quality text and then just add some noise to it by, let's say, deleting or replacing some words, and that can be useful as additional training data. Another useful property of machine translation is that it can output an n-best list of sentences. So it can output, it will output the most likely correction it thinks, but then it can also output other corrections that were still high probability, but maybe not as high as the other one. Sometimes the second or the third best translation actually might be better than the first one, so that's then useful. And another way of making use of machine translation is with multitask learning. So you can combine this with other tasks. So for example, you could build an error detection system to first detect where you think the errors are, and then you could feed that information into the machine translation system in order to guide it. Like, we've detected an error here, so this is a part of a sentence that you should probably focus on translating differently. And all of these tricks like improve the quality of the output. So the main advantage of machine translation is that it corrects all error types simultaneously. So you don't need to worry about, oh, am I going to correct just determiners or prepositions or so on? It just does everything at once. It also handles interacting errors, so there's no ordering effect, unlike some of the previous approaches. Again, it also does not require any feature engineering or expert knowledge, as long as you've got data of bad English to good English or whatever. It's a single end-to-end model and doesn't need any more details. And it's also one of the current state-of-the-art approaches. So like the best performing systems are often neural transformer machine translation systems, or at least some of them are. Now, disadvantages are, as I mentioned, it does require parallel data. Now, ideally, that's human annotated, but if that's hard, it can also be artificial. As a neural system, it can also take a lot of time to train and a lot of resources to train. So there's that to consider. You might remember I said the main advantages of rules are that they're interpretable. Well, machine translation is uninterpretable. It will output a corrected sentence, but it's very difficult to work out why it has made a change in a given place. Notable weaknesses of machine translation systems are that sometimes they will just change things like numbers without any kind of particular reason, which is a bit of a problem. Also, as an end-to-end model, though, they are hard to customize, which means if we want to add, so if we notice, for example, that the system is really bad at correcting, let's say, verb errors, it's very difficult to add a new component that just targets verb errors and improves it. Whereas if we want to do that for classifiers, we could just build another, like a new model or add some rules or something. So there are limitations to this approach as well. So the next one is neural edit labeling. And this effectively operates on the principle of we predict an edit label for every word. So if we have the sentence, they likes to eat the ice cream, you could predict keep for words you want to keep, and then replace for a word you want to change, or delete for words you want to get rid of, also insert if you wanted to insert a new word. And effectively, this is a classifier for every word. It's like part of speech tagging, where instead of predicting like this is a verb, this is a determiner, this is a noun, it's just predict what do we need to do to this word to make it grammatical. Like machine translation, it does also require labeled data, but in this case, you don't necessarily need the corrected form. You just need the label that tells you how to change it. And typically people start with a large language model, a neural language model, and then you can fine tune it to just learn the labels. Now, there is an open choice here in terms of what labels you use. So in the error detection, you could just have a binary, is this word correct? Is this word incorrect? In the example I've given, you could have 4 labels of replace, delete, insert, or keep. But there are also systems that add like even 5,000 labels where they will say specifically things like replace this word with the, replace this word with that, or just change this noun to plural, or different things like that. Now, one of the advantages of that are that, again, you can handle all error types if you provide the labels to do it. And again, because it's a neural model, it's a single end-to-end model. So you just input all the data and the neural model will learn how to handle it. Another advantage of it over machine translation is that it's actually more efficient. So whereas machine translation will have to predict a word at every given position, neural edit labeling only needs to predict a label, and that typically the number of labels is much smaller than the number of words that the model predicts. So it's actually a lot faster to run if you want to deploy this, for example, in a realistic setting. Unlike machine translation, it's also somewhat interpretable. So we might not know the reason why a particular label was predicted in a given position, but at least we know, like, well, we predicted change this noun to plural here, and so then as a human we can decide, like, do we want to apply that label or not, or at least we get a little bit more information about the kind of errors that are coming out, unlike machine translation, which is just outputs, here is a corrected sentence. And like machine translation, this is another state-of-the-art approach. Disadvantages, again, also like machine translation, requires lots of parallel training data, the more the better, but unlike machine translation, it does require a little bit of more engineering. So as I said, you need a human to decide how many labels we want the system to be aware of and what kind of errors we want it to be able to correct. An additional challenge is that it doesn't handle multi-token or interacting errors well. So for example, if you want to delete or reorder, let's say change the word order of a lot of words, this approach could probably only do it one word at a time, so you'd have to run the model several times in order to get to the end output that you wanted. Now, I'm sure everyone knows a little bit about ChatGPT, so language generation is kind of the latest approach to error correction that is slowly coming out. And broadly, it works by you train a very large language model on a very large amount of data and then fine tune on lots of natural language generation tasks. So this is huge. I mean, effectively, this is only possible by companies these days. Everyone is aware of ChatGPT, I'm sure, but it's also worth mentioning that there are several other models available, such as Bloom, Cohere, Google, and so on. Some of them are publicly available, some are not. Some perform better than others, some don't. But certainly the natural language generation approach is a new one that performs fairly well. So in terms of advantages to this, the generation approach is versatile. And this example with ChatGPT, so my town was located along the middle coast of Vietnam. It is a really beautiful place and has a lot of scenery. So on, it corrected it into very impressively fluent output. My town is located along the central coast of Vietnam. It is a truly beautiful place with stunning scenery. So in the past, so most error correction systems work on the principle of making minimal changes. Often it's important just to add a the here or change the tense of a verb and so on. And it's typically been considered much harder to like change the fluency of the output. Well, that is something that ChatGPT and other language generation approaches seem to be able to do very well. So we're certainly on the cusp of like a new era of correction systems that can generate more fluent output. That said, these models do also come with disadvantages. So firstly, not all corrections are errors. So in the previous example, the student wrote really beautiful and the model changed it to truly beautiful. Well, that's not a grammatical error. That's just a change of word. So you don't necessarily want that to happen. Also, it changed the phrase "has a lot of scenery" to "stunning scenery." Now, stunning scenery in that context was indeed more fluent, but "has a lot of scenery" also isn't wrong. So you don't necessarily want the model to be changing as much as it does. It's also important to note that the model can give inconsistent output. So there is actually a control in the model that determines how flexible it is with generating. If you input the same word input twice, you can get different output. And also, you might have heard about prompting. So the instruction that you give to these models also matters. So this wasn't ChatGPT, this was a different model, but if I gave it the input to correct the text, "I once go to the beach every day," and it output, "I once to go to the beach every day," so it missed the subject-verb agreement. If I then change it to correct the errors in the text, it no longer got the missing to in the infinitive. And then if I change that to fix the errors in this text, it got "want to go" perfectly, but deleted the full stop at the end for some reason. So these are complications that are definitely worth being aware of. Now, data and evaluation. Yes, so that's the end of the first part of how the approaches work, and the next part is on data and evaluation. So data briefly, so this is an overview of the different resources that are available to us for English error correction. You probably don't need to know this in too much detail, but useful things to know. So the FCE, First Certificate in English corpus, comes from English language exams, particularly at the intermediate level. So these are intermediate learners. Contains roughly 30,000 sentences, almost 500,000 token or words altogether. It was annotated by a single person or by a single reference, so there's only one set of correct answers. And each of these edits was annotated according to a framework of 71 error types. In contrast, NUCL, National University of Singapore Corpus of Learner English, is about twice the size. Again, one reference, except for this test set, which has got lots of different sets of annotations. 28 error types. So the authors were mostly undergraduates, Southeast Asian undergraduates. So the level was a little bit more advanced than AFC. And these were essays, particularly on topics such as like healthcare or technology. Lang 8 is a language learning website where people can submit, "How do I say this in English?" And then someone else who uses the website can come in and correct them. It's much larger than the other data sets, but it's also noisier because it wasn't professionally annotated, but just corrected by people on the internet. Also has the whole range of ability levels. And then finally, the Write and Improve plus Loch Ness corpus. So Write and Improve is a language learning website that we have at Cambridge. And one of the main advantages of this data set is that we specifically balanced it for different levels. So it's got roughly the same number of beginners, intermediates, and advanced students all writing exams on a wide variety of topics and from a wide variety of backgrounds. So this is the most representative data of learner English. Key things to know about these data sets. So there were some shared tasks, which I will talk a little bit more about later. In the first set of shared tasks, they only used the FCE dataset. In the second set of shared tasks, they only used the NUCL dataset. And in the most recent set of shared tasks, we used all 4 of these datasets. One limitation of these datasets is that all of them only really represent learner English. I mentioned at the start that, it's good to focus on learner English, but there are also other domains such as business emails or poetry or instruction manuals or whatever. So there have been some more work looking at building corpora for other domains. I also mentioned that the total amount of data is actually quite small. So there's only 1.1 million sentences, and not all of them contain errors. Neural models are regularly trained on billions of words, so this is not enough for that. And with that in mind, that's why people use artificial data generation instead. Now, there are lots of different ways of generating artificial data. So the first is rule-based generation. So if you start with corrected, or just, you could download some correct English text from, let's say, a news website. And then if you have a small amount of errors, you can go, oh, I know learners sometimes miss out the, or I know they get the tense wrong here. You can just apply some of those changes in reverse to the source text. So you can just artificially add some errors into it, either at random, or you could even match the distributions. If you know that, let's say, learners get determiners or articles wrong 10% of the time, then you can delete, let's say, 10% of the articles. Alternatively, you can also use a spell checker in reverse. So if you ask a spell checker to generate a correction for a word that's already correct, it will still actually output some alternative words. So you could then substitute them with similar words that are incorrect in that context, or you could generate them from a language model. Another approach is to do translation-based generation, and so it's back translation is what it's called, and effectively you're building a grammatical error correction system backwards, where you start with good text and you get your bad text. So you're training a model to add noise to the text, and then you can use that to generate like as much artificial data as you want. Another way to do that is round-trip translation. So you start with some English data, and then you can translate it to, let's say, Chinese with Google Translate, and then you can translate it back to English. And because machine translation is not perfect, you will end up with some errors in there, which this system can then fix, which you can then use as training data. Now, I'm going to talk about evaluation metrics a bit. So GEC systems are often evaluated in terms of edit overlap. So if we have the sentence, "I often look at TV," then the correction that a human made would be, let's say, replace "look at" with "watch." Now, different systems will output different things. If the system exactly matches what the human did, it'll get a point for correction and all types of detection. If the system wants to replace "look at" with "see," then it will not get a point for correction because it's not output the correct word, but it has at least detected the error in the right location. If it only wanted to change, let's say, "look" to "watch," however, then it doesn't get a point for correction because the correction is wrong. It also doesn't get a point for span detection because it's not identified the full span of the error, but it will get a point for at least detecting like partial error. The problem, however, in error correction is that most systems output corrected sentences, and so we don't have access to the edits. So in this example, this is grammatical sentences. If a system produces this a grammatical sentence, we don't have the information that goes, oh, what was replaced where with what, which we do have in the reference. So this is the main problem in evaluation, and so I'm going to now tell you how to solve this problem. So it's effectively an alignment problem. So if we've got the sentence, "the most big parrot also can do a talking," with the reference, "the biggest parrot can also talk," we now want to work out which words should be aligned with which other words in a way that makes sense. I've shown two examples of how you can do that. So we could align most with biggest, big with parrot, parrot with can, and so on, which doesn't make any linguistic sense, but is a possible way of aligning these words. Although I hope we would agree that we'd want to align big with biggest, parrot with parrot, and talking with talk, because that just makes more sense. So this is effectively the problem. Now, the way you solve that is use something called Levenshtein alignment. It's also used for spell checking, and in effect, the alignment is calculated in terms of cost for changes you make. So if we wanted to change cat to cart, we would insert an R, and the cost would be 1. If we wanted to delete a word, a character, that would also be a cost of 1. If we wanted to replace a character, then there's a cost of 2, because it's effectively an insertion and a deletion. And if we wanted to reorder 2 characters, that's another cost of 2. And if you use this framework, you can then calculate different ways of combining aligning these sentences. So if we apply that to our previous sentence, this is a possible alignment. We end up with 4 substitutions for a cost of 8, plus 3 deletions for a cost of 3. 8 plus 3 is 11. If we then do it with our preferred alignment, we end up with 3 substitutions, 6 plus a transposition, 8 plus another 3 deletions, 11. So the problem here is that using this algorithm, both of these alignments are exactly the same, which is not what we want. So we then need to solve this problem. Now, there are the first way of solving it is by using something called the max match scorer, which is one of the most popular evaluation metrics. And effectively, it tries to find the alignment that maximally matches the reference edits. So if we know that a human edited the sentence specifically in this way, so they changed the words 1 to 3 to biggest, 3 to 4 to parrot, and so on, then we can try and find the alignment that maximally agrees with what a human did. An example of that, so we have lots of errors in this space, and this is one way of splitting them up. We could change most to biggest, big parrot to parrot, and so on. And if we do it this way, then these two do not match the human references, but these two do, which means that this is certainly a better alignment than the previous one. We can also try aligning it in different ways, such as this. And in this case, we now get 3 of the edits matching a human. So 3 is larger than 2. So the M2 scorer will prefer this alignment to the previous one. And then if we wanted to fix it, we could just remove this line here, and then we would exactly match the human. So that's effectively how the M2 scorer finds the best alignment. An alternative approach is to use Errant, which was my PhD. And all that really happens here is I add some linguistic information into the alignment. So first, we automatically pos tag and lemmatize the text, and then the only thing we change is the substitution cost. So you may remember the deletion and insertion cost is 1, and transposition cost is 1. Instead of having substitution cost as 2, we change it to a cost of, are the part of speech tags the same, are the lemmas the same, and how many characters are in the 2 words. So it still sums up to a range of 0 and 2. So the cheapest is 0, the maximum cost is 2. And to give an example of how that works, so if we align most with biggest, so the part of speech are different, so that's 0.5. The lemmas are different, so that's 0.5 with 1. And so the characters, I mean, both words end with ST, but the rest is different, so that's still quite a heavy cost. So total cost 1.72. In terms of big to parrot, again, part of speech are different, lemma are different, no characters in common, maximum cost of 2. Whereas if we look at can talk at the end, now both of them are verbs, so it's cheaper, but the lemmas are different and the characters are different, they only share an A. So effectively, this is how we get the different scores, and that ultimately gives us a cost of 9.77. If we then do it with our target ideal alignment, you'll see that the cost is much less, because in this case, big to biggest, where the part of speech is the same, the lemma is the same, and the only difference is we're now adding GEST, so there's a character difference. Again, parrot, again, quite cheap because the character difference is small, and effectively, like, this is just the way of finding the best alignment out of all the possible alignments. An additional thing that Errant does is it also adds some merging rules. So we might, like, often not all errors are like 1-to-1, but we want to expand them. So for example, probably don't want to just delete most and change big to biggest. A human would probably say change the phrase most big to biggest. So there is a rule to combine them. Similarly, doer talking, like you can't just change talking to talk. Doer talk might not work. So there are ways of just combining these into more human-like edits. An additional strength of Errant is that it also does error type classification. So again, based on the part of speech, lemmas, similarity between the words and so on, we can automatically work out like what type of error this is. And error typing is very important because it not only allows us to do detailed evaluation for systems, so for example, system A might be better at spelling than system B, but also for humans. So an application in the classroom, if a teacher corrects all the errors of the students, you could then run Errant on it and work out which error types they are weak at, Maybe human A is really bad at prepositions, but human B is really bad at articles, or maybe the whole class is bad at articles, so you could then use that to teach them or reinforce that. So once all the edits have been extracted, we then combine all the information into a single score called the F score. So if we have an original sentence here, the most big parrot can also do a talking. A system might output the most big parrot also can do a talk. So it's not got everything, it's got some things, but then we can use either the M2 scorer or Errant to extract the edits here, and then we also have the human reference edits here. So then it's just a case of comparing the two sets of edits, as I did in the first slide of how evaluation works. And the way that they are combined there are things called precision and recall. So you measure recall as the true positives in green out of the total number of true positives to false positives. So effectively in this case, the green one, so the system said change 3 to 4 to parrot, and the human agreed, so that's a true positive. But the system also suggested changing talking to talk, which was not correct. So you get 1/2, 0.5 per precision. For recall, it's the same thing, but here, so again, the true positive is 1, but there were 3 other edits that the system missed, so it only gets 0.25 for recall. And then both of these scores are combined together into F1 score, which gives you an overall score of 0.33. I mean, you don't need to know too much about the details of that, but this is just an overview of how we can evaluate an error correction system, or what the most common ways of evaluating it are combined into a single number. To give a more concrete example of system output, so this was the best system in the most recent shared task in 2019. And here is a breakdown of performance on lots of different error types. So it remains to this day, so correcting adjective errors, adverb errors, noun errors, and verb errors, they are typically the hardest. And that's not really surprising because they're content words. So that means the system really needs to understand the semantics of the text in order to propose a correction. And that's like semantics is just one of the hardest things for these models to do. In contrast, it does very well at spelling errors, as you would hopefully expect, and also in like morphology errors. So, I mean, tense was a little bit trickier, but subject-verb agreement performance is very high. Inflection is very high, but relatively rare. Verb form errors also very high. Similarly, like noun number errors, very good, and adjective form errors also very good. So this really gives us more information about how well these systems do. I mean, determinant errors, as you can see, are also very, very common, but the system still does very well. And similarly with prepositions. So this is just an example of what you can do with the evaluation and how it might inform your system development or human evaluation as well. So now on to the final part, shared task, current trends, future challenges. So I mentioned these shared tasks a few times. So effectively they're academic competitions where everyone is given the same data to build a model and just have to do as best as they can. They don't get given the test data that is hidden. And so then it's just a race to who can build the best system in like 1 month, 2 month time. And then we evaluate it independently and see who performed best. Now, the first shared task was helping our own in 2011. And in that task, they asked everyone to correct all the error types in the sentence. And the best score was only 20, and most systems didn't even reach 10 F1. So this is out of 100 as well. So like the task was very difficult to the extent that the following year they simplified it a lot and said, okay, we can't correct all error types yet. Let's just correct articles, so the an, and prepositions. And that just made like still only 29 F1 as the highest score, but still at least it was a little bit easier. The following year there was the Connell 2013 shared task, and that again increased the complexity. So in addition to articles and prepositions, they also said participants should correct noun number errors, verb form errors, and subject-verb agreement. And this time the score went up a little bit further, but still not very good. And at this time, so language models and classifiers were the best approaches at this time. Following on from that, there was the CONL 2014 shared task. And again, this returned to let's correct all error types. And this time the score was 37, FO5. So I mentioned F1 as a way of measuring. So the difference between F1 and FO5 is that precision is twice as important as recall. And what that effectively means is it's more important that a system make like valid corrections than to necessarily correct everything. It's much worse if a system suggests something and gets it wrong than it is for the system just to not notice something. So that was the intuition there. This shared task also had two sets of reference annotations, and so there were two possible correct answers to match. And this time the best systems were classifiers and machine translation for the first time. Then the most recent shared task, again, was all error types. This time the score was much, much higher. That was partly because there were 5 sets of reference annotations, because it was considered important to have lots of different possibilities, given that there are multiple ways of correcting a sentence. It was also important that this was the first shared task to have the diverse data set of beginner, intermediate, advanced, and native errors, unlike the CONL shared task, which was only like university undergraduates in Singapore. And all submissions were also machine translation, but they were transformer neural machine translation. Both of these two data sets are still the benchmarks, so all progress tends to be measured on these data sets even today. In terms of recent work, so these are the latest scores, or the highest scores on these data sets to date. And for comparison, I've got the scores from the shared tasks in the past. I mean, as you can see, there's a massive increase on CONL 2014 and even a 10-point increase on BEA, which just shows how much like performance is increasing over time. That said, this best model actually just combines the output of 5 different models. So different approaches have different strengths and weaknesses, and it's a valid strategy to build 5 different error correction systems and then work out how to combine them. But that then might not be practical because you'd have to wait for the system to, like each system to process it. So there's a kind of caveat there. And in fact, all the top 3 best systems ensemble, so that ensemble means combined multiple systems together, using different pre-trained language models. So you might have heard of BERT before ChatGPT, and then there's also others such as Roberta. There was an early form of GPT as well, and also XLNet. In addition to that, so edit labeling approaches are also competitive. So there's both the translation approach and the edit labeling approach. Both perform equally well at the moment, although, as I said, we can see how approaches like ChatGPT are going to change in the future. Some observations. So there is no obvious relationship between artificial data and quantity and performance. So it's very difficult to generate good artificial data. I mean, yeah, so it's easy to generate, but then you want to constrain it in a way that it matches human errors. And so it's not practical. If you just delete random words, then that's not the kind of errors learners make. Learners aren't just going to delete random words. They always delete very specific words for very specific reasons, either based on their first language or whatever. Different models have strengths and weaknesses. I think I mentioned this, how to combine the models, but is that practical to combine so many things? And at least in the academic literature, there has been too much of a focus on just beating the best number. I mean, sometimes it might be better to have a system that is just easier to run and faster, that doesn't necessarily get the highest score, but then is at least more useful to teachers or people in general. It's not just about building the most complicated system. So to wrap up a little bit, I see we're hitting the hour. Future challenges. So one is domain generalization. So as I mentioned, most of these systems have been designed with language learning in mind, But it's also important to consider error correction systems for other domains, such as business or documentation or literature, poetry. Personalized systems is also important. So, I mean, as English language teachers of Vietnamese students, you probably want an error correction system that adapts to errors specifically made by Vietnamese speakers rather than, let's say, Spanish speakers or other speakers, but also ability levels. Like, you will want a different system for beginners versus advanced speakers, and that's something useful to do, personalize these systems. Feedback comment generation, so explainable AI, that's another very important area at the moment. Most of these systems will just output the correct answer. You don't necessarily want that, though, and in fact, most teachers I've spoken to will want the first step to just be a system that detects an error and then asks the student, I found an error here, go away and think about it and see if you can correct it yourself, because it's much better to, like, you give that reinforcement feedback of fixing your own errors rather than just relying on a machine to correct everything for you. Semantic errors, I mentioned those briefly as well. So these systems still struggle with like complex things like idioms, multi-word expressions, collocations. So there's definitely room for improvement in those areas. Contextual GEC, so most systems operate at the sentence level, so they will just correct each sentence one at a time. But I mean, some errors depend on the previous sentence. So if it was Tom went outside, she was happy, then you need to know that actually, no, she refers to Tom, and so it should be he. But error correction systems won't correct those kind of errors very well at the moment. Other challenges, so system combination. So we talked a little bit about that, but there definitely should be ways of finding which systems have complementary strengths and which cover weaknesses in others and combining that in a sensible way. Training data selection. So the data sets that we have often have lots of article errors in. Now, that could be useful, but at some point you have to ask, when has the model seen enough examples of article errors? Do we only need 100 of them in order to correct them? Do we need 1,000? Do we need 10,000? Do we need 1,000,000? And so at some point we have to work out, like, what is the most optimal use of training data? We don't necessarily want to just create as much as possible, but we can create it in a more targeted way that represents the kind of things we want to capture. Unsupervised approaches, so I mentioned human annotated corpora are expensive to create, so we definitely want to encourage research into approaches that do not rely on this human annotated data. Multilingual error correction, so just like we have systems these days that do multilingual translation, that can translate English to French, French to Spanish, Spanish to Vietnamese, it could also be useful to develop systems that not only correct other languages as well, but maybe correct multiple languages at once. And then finally, improved evaluation. So evaluation is currently carried out in terms of edits of tokenized text, but ultimately a user will only be seeing untokenized text. And we might also want to display like possible alternatives. So if you imagine like Microsoft Word, it will, if you right click on a spelling error, it'll say, did you mean ABC? Error correction systems currently don't do that. They will just give you the one best answer when actually there might be multiple answers. So it would be useful to encourage systems to do that. So finally, I just wanted to mention the multi-GED shared task. So there's another shared task happening at the moment. And this is the first multilingual shared task. So we've gone beyond just English for the first time. And it's specifically focusing on European languages, Czech, English, German, Italian, and Swedish. And the goal is to identify the errors in a sentence. So which words are correct, which words are incorrect. And here's an example. They likes to visit town, and you could so the system should output incorrect for likes and also town in terms of identifying a missing word here. you probably like this is happening literally right now, and we're releasing the test data next week. So it'll be interesting to see what happens with that, and whether people are able to build the first multilingual detection systems in the future. And that is the end. We hit about an hour exactly. I hope that was informative. And yep, any questions or comments, I'd be happy to answer, particularly in relation to how these tools could be used for education as well. Yes.
Thank you, Chris. Thank you for a very helpful presentation on your work and also on the implication that it might have for English teaching and learning. So now the floor open for everyone. If you have any questions or any comments throughout the talk, please just raise your hand or unmute yourself and feel free to come in at any point.
You can also write them in the chat if you prefer.
So everyone probably still thinking about the questions to ask. So I have some questions for you. So I think this is a very helpful overview of how the system of error correction works. I'm wondering what you think about its implication for English teaching and learning in particular. Specifically, were the system initially built to replace teacher entirely? Can you see a future where basically we don't need English teacher to correct the text for the student anymore, but we can rely entirely on this automated system?
That's a very good question, and I can reassure everyone with 100% no. These systems are never going to replace teachers. They're always billed as or advertised as like supporting teachers. So as I mentioned at the start, a teacher can't possibly correct all the errors that every student makes all the time. And so particularly like when you're sleeping, if a student writes an essay and they want feedback, then they would have to wait for the teacher to look at it. Whereas with these systems, you can just put it into the system at any time, and hopefully the system will give you some sensible feedback. And it won't necessarily correct all the errors, but it should correct some of the errors, which means by the time that the student does give it to the teacher, hopefully it's easier for the teacher to correct because there's fewer errors to fix. And also, as I said, it's also important to think about how to customize these systems. So instead of just correcting all the errors immediately, for educational purposes, it could be just alert students to where errors are and see if they could fix them themselves. Because I think it's definitely more important that people learn from these systems rather than rely on them completely. Yes.
Yeah, thank you. I have a follow-up question to that as well. So you build a classification system, which is basically can classify error type, which I thought was really helpful for English teachers. So how usable are they for a normal English teacher? Let's say if I have a class of English students and I have corrected that text, and can I easily run that system on these output to basically get a sheet of, let's say, how many % was adjective error, how many % was article error, so I can just get an overview of the competency of the student, like how usable is it for an English teacher with no computational knowledge?
So currently, unfortunately, I would say not very. That said, like that's something that I've wanted to do for a long time, and we have actually built I built a prototype quite a while ago. But yes, and that worked exactly as you would hope. So effectively, you would ask the students to fill in essays like online, and then all of that goes to the teacher. And then the teacher can just edit or make some changes to the essay online. Then you could hopefully just hit a button. It would run errand and everything behind the scenes and extract all the edits and all the error types, and then give you a breakdown of how, like, what errors the students made. I did have a little demo video of that a while ago, but I don't think I can find it in time, unfortunately. But I could send that across if everyone's interested. And particularly so, I don't get to speak to English teachers very often. So if that's something that you would consider useful, like certainly that's something to talk about. Like if you think this kind of system that will automatically tell you what kinds of errors your students are making is going to be useful, then like if there's enough of a demand for it, maybe that's something we could build.
Yeah, what does everyone think? Because I have less experience teaching English than a lot of people here. So maybe it's better to let them tell you how necessary that is as a tool. Because conceptually, I think it would be very helpful. Because when I correct student essay, I don't want to having to actually do the calculation myself of what type of error they're more likely to make. Because I can see that it's very time consuming, but it's really helpful in adapting the curricula. So if you know that a particular group of students are very weak at article errors, then maybe you can change the curriculum slightly to sort of adjust to that and help them improve that particular area. That more kind of like a targeted learning. But I don't know how useful it is for teachers here who are actually on the floor teaching students. So maybe if someone can tell Chris a bit more about that, then that would be very helpful.
Yeah, to reiterate, the goal of all of this technology is to support and help teachers. We never want to, there's no replacement ever going to happen. It's always about whatever will make teaching students easier. That is the focus, and that's always what we try to do. And so, yes, hearing problems that you might have with teaching, or at least ways that you think you can automate teaching and make your lives easier, are always good to hear about.
Yeah, Yi, please feel free to unmute yourself.
Hi, so thank you so much for a very informative talk. So I usually employ indirect corrective feedback in my writing class. I think it's really beneficial because students can, it can help students to improve their metacognition, so they can know what is the mistake and they can correct it later, and so they can self-regulate their own learning. So I would like to ask, are there any kinds of apps or websites that can help feedback automated system, so I can use it in my class and save a lot of my time? Thank you.
Good question. And yes, absolutely. I mean, I have to talk about Write and Improve, Cambridge English Write and Improve, because that's the one that we develop in Cambridge. And I mean, I don't know if I can, maybe I can show you a quick example. I'll share my screen again. Oh, I don't know if, so here we go. This is the Cambridge English Write and Improve website. I don't know, can we just go straight in? Yes, so you go right in, ask what level you are. Let's go with intermediate. And then it will present you things like, it give you a task, ask you what to do. That's, how do I do this? I mean, it wants 100 words. Let me see if I can just find some words somewhere that are going to be off topic, but at least an example. Oh, you should enter. Oh, okay, good. And then it's checking. Oh, there we go. I got an award. Continue to feedback. So because this was grammatical text, it probably not picked up many errors. Yes, it's not picked up any errors at all. But it gives you a score for whether you answered the question correctly or like whether you were on topic. If we let's add some errors in here. I can ask it to check again. Okay, it didn't notice these, but I mean, I think that's because I'm giving it like unexpected input. But certainly, if you have your students write things like this, it will also try and highlight some errors and make them think about it, and also give them feedback. So yes, so this graph down here will also show you how your level changes over time. So for example, if your first attempt was relatively basic, it might give you a low B1. And then if you add more complex vocab or structures, then it might increase your level predicted over time. So yeah, that's an example of the tool that we develop. And yeah, probably worth looking at and hopefully helpful.
Yes, Hương, please unmute yourself.
Thank you, Mr. Brian. So I just would like to ask, like, which approach do you think would be more effective for students who